All right, let's try this again. This didn't record the first time, sadly, so this will be a faster version because everything's already written out, which is fine because a lot of this we've done. This is a practice day. So this is our first Taylor series FRQ. Um, Typically, they work like this. You're going to either build the Taylor series or they're going to give you the Taylor series. You're going to find the radius or interval of convergence. You're going to do something with the series, either finding the derivative or integral or something. And then there's usually an error bound type question, which we haven't talked about yet, or some other kind of question like this one, which we'll see today. All right, so let's go through this. It says the Taylor series. As soon as you see the word Taylor series, that means the series represents a function. So the series is an actual function that is out there in the world that we could write, like e to the x or natural log x or sine of x or cosine of x or 1 over 1 or something. So if it's a power series, that means there doesn't have to be a function form for it. But because this is Taylor series, that means we know there's a function out there that represents it. Then it says it's about x equals 1. That just means the center is at 1. So it's centered at 1, and we can see that from this term right here. X minus 1 means the center is at 1, which means it's most accurate when you plug in values closer to 1. And converges to f of x, that just like I said means it represents a function. So its sum, if you will, this is the same thing as saying it converges to f of x. Its sum is some function. And they say this piece, which says that r is the radius of convergence, that's just the thing we've seen a bunch. There's a radius of convergence and an interval of convergence for this Taylor series. Okay, so part A, find the value of r, aka the ratio test. And this one's kind of cool because you don't even have to test the endpoints. All you have to do is find the radius of convergence. So notice we're pretty good at this now. I set up the ratio test. I moved the x minus 1 to the n up by the 2n all over n. I did not include the alternating component because that term cancels out anyway. And every exponential should cancel, every factorial should cancel, but there are none of those factorials. And all your polynomial terms like n and n plus 1 do not cancel. They stay there, and when we evaluate the limit, we then don't have to worry about them. So notice we are left with a 2 after we evaluate the limit. And after I pull the x minus 1 out of the limit, and that means I get a radius of convergence of 1/2. And that would be sufficient for this problem. But I went one step further. I found the interval of convergence by splitting it and then adding 1 to both, and then I tested the endpoints. Now, when I plugged in 1/2, I got negative 1/2 times 2 to the n. I can combine these together by writing it as negative 1 times 1/2. And then 1/2 times 2, put them inside the same n term, and they just basically cancel out. They become 1 to the n. So you're left with a negative 1 to the n and a negative 1 to the n plus 1. So does this mean it's alternating? Well, here's what I did. I combined them together into a single negative 1 by adding the powers. And you get this exponent, which is always odd. So in other words, the top is always negative, which means this is just a harmonic with a negative on it, and that diverges. So 3/2, similarly, I plugged in 1/2, I plugged in 3/2, and 3/2 minus 1 is 1/2. 1/2 to the n and 2 to the n just cancel out. They make 1 to the n, and that 1 to the n is just 1. So this was the alternating harmonic because this is an alternating component, and that converged. So this would have been the interval convergence if they had asked for it. Okay, the second part. They say find the first 3 non-zero terms and the general term of the Taylor series for the derivative of our series. So essentially, they're just asking us to find the derivative of this series. So I think the best way to do this, here's the series, I just rewrote it. This is the series for f. I expanded it out by finding 4 terms. How did I do that? I plugged in 1 and got this term. I plugged in 2 and got this term. I plugged in 3 and got this term. Plugged in 4 and got this term. Then what I did was I took the derivative term by term. So the derivative of 2 times x minus 1 is 2. The derivative of this is a power rule, and this 2 cancels with this 2, and you're left with this term. The derivative of this one, the 3 cancels with the 3, and you're left with 8. And then you decrease the power, and so on. We have a nice little pattern here. So, how do you find the general term, though? Well, here's what I went through, and sadly, I'm going to have to kind of shorthand this, and this will be practiced in the future a bunch. I like to do this a few ways. Well, one kind of starting off point. I notice it's alternating, and if it's alternating, that means I'm going to include an alternating component. Now notice I have this in n without the plus 1. The plus 1 was in a different color. I started with just, actually let's start this over. I started with just this. Then I noticed I had powers of 2, So I put 2 to the end, and I noticed I had powers of x minus 1 to the end. So a lot of students will stop here and be like, I did it. But you need to test your general term and see if it's working as it's supposed to. So right here, I said, look, the sigma notation started at 1. So when I plug in 1, I really would like to get this first term. When I plug in 1, I get a negative, and I don't want a leading negative. I want a leading positive. We can fix that by just increasing this by 1. What about 2? When I plug in 1, I get 2 to the first, which looks good. So that seems like it's okay. And then what about x minus 1 to the end? Well, when I plug in 1, I get x minus 1. I don't want an x minus 1 term. I want it to be x minus 1 to the 0, so that when I plug in 1, this term goes away. So we can fix that by plugging or setting it to minus 1. And now look, when I plug in 2, let's test the next term. Negative 1 to the third is negative. 2 to the second is 4. And x minus 1 to the 2 minus 1 is x minus 1. So that general term works. So what am I doing down here? Well, in this point, I'm actually trying to just take the derivative of the original general term. You can try it that way too, rather than building it from the expansion. You can try just taking the derivative. So I did the power rule. I swung the n to multiply it by this. That's how I got this term right here. Everything else stays, and then we just decrease the power on the x minus 1 term by 1. And look how nice the n's canceled. And yes, we really do get the exact same general term we just had a second ago by looking at the series expansion. You're going to have to know how to do both these strategies. Different problems rely on one versus the other. Okay, so that was step 2. Find the derivative of the first 3 terms. We didn't even need this one. And the general term for the derivative. Now, part C is interesting. It says the Taylor series for the derivative found in part B, so that we found the series in B, is geometric. And I mentioned that if it's geometric, that is super, 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 super important to pay attention to. Because if it's geometric, that means there's a ratio we can find, and there's a first term we can find. And we can plug it all into a sum formula, which will give us the function formula, which is really nice. So it's telling me that the series I just found is geometric. Is that true? Well, the first term was 2. The next term was this minus 4 times x minus 1. The next term was 8 times x minus 1 squared. Yeah, it looks like I'm multiplying by negative 2 times x minus 1 to get from one term to the next. So I have a ratio. I have my first term. This series converges to the derivative function of the original because I started by taking the originals and finding the derivative. So, in other words, I can rewrite this using the sum formula because the function and the sum formula are essentially the same thing when you're dealing with a power series like this. So, it is the first term over 1 minus the ratio. The sum is the closed form function form for the Taylor series. And then I cleaned it up and I got to this point in black. And then what am I doing here? Well, it's asking me to do something. It's saying find the function f prime to which the series converges, and then use this function to find the original. So how do we go back to the very beginning? We take the antiderivative of each side, and the antiderivative of this is just a natural log absolute value of 2x minus 1. And we actually found the original function that this Taylor series represents. So if I had you build the Taylor series for this function in the bottom, this thing, you'd get that original Taylor series that the whole problem began with. So this is a good FRQ, a little bit tricky. It all hinges on, can you find the radius of convergence? Can you take a derivative and find the general term? And then can you recognize that a geometric has these 2 components? And by recognizing that, you can plug them back into the sum formula to get the function. All right, that was it. We will do a lot of practice FRQs starting pretty much now. All right, that's it.